term measurement just should not appear in a fundamental theory because it's not a fundamental notion.
Mm-hmm.
It's like pianos. I mean, there are pianos, they exist, that's okay, but you shouldn't have to mention pianos or have to figure out whether a collection of atoms constitutes a piano in order to figure out how the laws of physics go.
Hello, this is Robinson Erhardt, here with the introduction to Robinson's podcast number 188. And this episode is with a couple of old regulars on the show now. Those are Tim Maudlin, who is professor of philosophy at NYU and founder and director of the John Bell Institute for the Foundations of Physics, and one of his BFFs, Sheldon Goldstein, who is distinguished professor of mathematics at Rutgers, where he researches mathematical physics and the foundations of quantum mechanics. Shelley, naturally, then is also board member of the JBI, and this is his second appearance on the show because way back, like a month ago on episode 170, we talked all about Bohmian mechanics. And then on the other hand, this is Tim's fifth appearance on the show. Tim was a guest, and I am going to list them all. He was a guest on episode 46 on laws of nature, space and time, and then 67 with David Albert on the foundations of quantum mechanics, 115 with Craig Callender on the philosophy of time, and then most recently, episode 142 on Bell's inequality and the philosophy of science. But in this episode, we get into a bunch of other fun big words, including the Copenhagen, which I occasionally pronounce Copenhagen, interpretation of quantum mechanics, the many worlds theory, spontaneous collapse theories, and then most importantly for these two, Bohmian mechanics, and then also emergent relativity. If you're interested in the foundations of physics, which you almost certainly are if you're listening to this episode, then as I have said before and will certainly be saying again, please check out the JBI. There's a link in the description, which is devoted to providing a home for these sorts of conversations, and this research and any donations are very helpful for them. Speaking of donations, there is a Patreon that you can join for this show with ad-free episodes and show notes. There's a link to that in the description as well. And now, without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Tim and Shelley. I suspect that there could be many references to past episodes in this conversation, or even to future episodes. But in my last conversation with Shelley, I mentioned a conversation prior to that conversation with David Albert, in which David said that for much of the last 100 years, the metaphysics of quantum mechanics has been held back by Bohr's legacy and the Copenhagen interpretation, but that David's work and your work, Tim, and Shelley and Barry Lowers and Nino Zengi's and so on has really undermined this. And now there are other interpretations on the table. But Shelley said that he still thought Copenhagen was dominant, or might be dominant, not just among physicists, but among philosophers. And so, Tim, I wanted to check with you to see if you still think that's the case. And Shelley, if you think...
I'm not so sure about philosophers.
Okay.
Yeah, I
really know better about philosophers.
Yeah, I guess... I mean, first of all, let me just say it was a very lovely list of people, but, you know, again, it was really Bell, I think, who sparked proper, rigorous discussion of these issues and kind of blew away a lot of the rhetorical clouds that had been standing in people's ways of clearly understanding what the issues were. And we, to a large extent, were picking up from him. Yeah, so there's the sociological question. I think it's quite true. I think it, quite honestly, would be hard to find philosophers of physics who are out defending something they would call the Copenhagen interpretation, or out defending Bohr. I mean, there's a few people nowadays who are kind of in a sort of retro way going back to try to rehabilitate Bohr. But I would say the overall sense is that you can map out different approaches, and Copenhagen isn't among them just because it's not clear. I mean, the one thing as a philosopher you want is clarity of even what you're talking about. And with Bohr, as Shelley said, you just don't have that. So I don't think there are many philosophers of physics who would step up and say they're Bohrian. There's a little bit of this epistemic stuff that floats around that, among the physicists goes under the name cubism, and some certain kind of pragmatic strands that show up here and there. But I think probably most philosophers of physics are on the same page about what the options are that are in a situation to be worthy of serious discussion at this point. As for physicists, I think they're happy to have some words they can say and then try and change the subject. I will mention one data point, which is that Adam Becker, when he wrote his book fairly recently, What is Real, and he has a physics background, and he gave a lot of talks in physics departments, and he was expecting very strong pushback against criticisms of Copenhagen, and he said he didn't get it. He said when he criticized Copenhagen in front of physics departments, he got a lot of nodding heads of people saying, yeah, we never understood it either. Not, yes, this is the key, to understanding everything. So that's not from me, but from him. He was expecting much more pushback, and it didn't come.
David mentioned that some of Bohr's papers were so unclear and unreadable that for years a couple of pages were transposed, or one was missing or something like this, and no one noticed.
They're switched, in the big red volume, in whatever it's called, quantum measurement, and I don't know, the Zurich volume that reprints all these papers.
Mm-hmm. Well, it really suggests a lack of clarity if that wasn't totally obvious. Then this begs the historical and sociological question of why Bohr had such an impact on discussions and the practice for so long before Bell, as you mentioned, was the main person who dispelled this.
Look, we're now in historical territory I don't feel at all as secure about, but unlike David tends to read Bohr as just an instrumentalist. I don't. I read Bohr as somebody who grew up steeped in neo-Kantianism. I think, there are things that he says that, to me, if he was raised with a bunch of Kantians around talking about what it is and is not anschaulich, that makes a lot of sense out of some of the things he writes. And tell me why Kant has been so popular, right? I mean, in philosophy, why has Kant had such a huge impact when he's pretty incomprehensible? I mean, nobody thinks you can just sit down and read the critique and understand what's going on in it. But nonetheless, he's had this huge impact in philosophy that continues to go on, partly because of the obscurity. There's a certain level of obscurity and Gnostic pronouncements that come across to people as deep and profound, which I'm not built that way myself, but, lots of people are. We certainly know in philosophy, lots of people are.
Robinson, have you read Bohr's writings?
I have not.
It's worth making an effort just to get a good sense of how incoherent they tend to be. And this raises the question, number one, why did physicists themselves, who are very smart people, not provide a sharp critique of what Bohr wrote? And it raises certainly the question of why philosophers who are supposed to be in that business tended early on to rarely give a sharp critique of what Bohr wrote. There was a failure in both communities, I believe. The only person that I'm aware who actually bothered to give a sharp critique, and it was devastating, it was basically 1 or 2 paragraphs of Bohr, was John Bell. But the literature should have been full of stuff like that, because Bohr was such an inviting target in this respect.
Mm-hmm. It's sort of, granted, as you pointed out, I haven't read it, but it still sort of reminds me of the Sokol hoax, which I talked about with your colleague Tim Paul Boghossian, but essentially this nonsense paper was accepted by some prestigious postmodernist journal and nobody batted an eye. But it's interesting that ostensibly nonsense thought could become dogma in a field like physics where nonsense is anathema.
Yeah, I mean, there may be a historical, I mean, let me give a piece of what may be the correct historical account. Again, I'm not confident about this. The development of quantum mechanics goes through a bunch of different phases, and a lot of people go back to Planck. But when you read Planck, it's clear he didn't really know what he was doing. I mean, he found a mathematical technique that got him the answers he wanted, and he didn't even have any clear view about why it worked or what it suggested about the physical world that it worked. And then in 1905, Einstein, ironically, given how much he really disliked what happened with quantum mechanics, I think really kicks the thing off with his paper on the photoelectric effect. But David often talks about this other problem about the stability of matter, because just naively using Maxwellian electrodynamics, you would expect that if the electrons were orbiting the way we draw pictures of them orbiting, they should radiate out energy and crash into the nucleus. Now, there was something called the old quantum theory. So this is in the teens that Bohr came up with, which were just a bunch of numerical rules for allowable orbits that you could kind of motivate as not being unreasonable, but didn't have anything deep underneath them. So Bohr says, well, what if the orbits have to be confined to this discrete set of orbits and electrons can only jump between them, and they have different energies, and when they jump, they emit or absorb only the amount of energy that's the gap between the two. Okay, so that's the old quantum theory. That's a kind of relatively clear sketch of a picture, but it immediately raises the question, but when and why and how do the electrons jump from one orbit to another, right? I mean, then that's just a good physical question. How does it go from orbiting this way to orbiting this way, right? What's the transition like? And so they kind of beavered away at that for a while, but they couldn't make any progress on it. And then the new quantum theory basically comes with giving up on questions like that. Just, we're not going to ask them. They're no longer legitimate questions. Now, if you've been banging your head against a question for a while and not making any progress, you're in a good psychological state to be receptive to someone saying, that's not a good question, right? Stop trying to answer it. And then what does Bohr back that up with? Well, all the stuff about what is and is not unschaulich, which goes back to, what you can visualize. And we've reached the end of visualization. And the only reason that you're looking for these exact trajectories is that you're thinking that things are visualizable when they're not. But Kant told us that visualizability has to do with human sensibility, blah, blah, blah. So I think you could tell a story where people would welcome the obscurity because it was an escape from a bunch of technical problems that they didn't know how to solve and got them out of them, right? Not by solving them, but by telling you a little fairy story so you didn't have to solve them. I mean, there's this famous quote by Einstein. Shelley wrote that, read that other quote on your interview with him. There's a famous quote in a letter much later, I don't know, maybe in the 40s, when he talks about how all the physicists are asleep. They've been lulled away on this pillow of quantum philosophy. I don't know the exact quotes. And it's better just let them sleep. We can't wake them up. And I think he had his finger right on the thing. People didn't want to talk about this stuff because they didn't know what to do with it. and they were kind of getting along without it, and they just don't rock the boat, right?
But there was a little, maybe it was the authority of Bohr somehow which scared people from talking about this stuff. I don't think the physicists in this street would have been quite so intimidated were it not for the authority of the leaders, Bohr, maybe Heisenberg. What was going on between those two is not so clear. A lot of competition, an unhealthy situation, no doubt. Einstein and Schrodinger never bought for a second any of the Bohr nonsense, but not for a second. But for some reason, people tended to not side with Einstein or Schrodinger, but Bohr for reasons I can't really understand, but I can emotionally feel, because I myself, knowing so little, felt I wanted to side with Bohr. That was not because I knew so much, because I knew so little. Maybe if you knew enough, you'd have the confidence to know you shouldn't be siding with. I wanted quantum mechanics to be the revolutionary thing we were being told it was. I really wanted that to be the case. I'm not proud of that, but that's how I felt. And I suspect that's how many physics students and physicists ended up feeling. Bohr, by the way, did get the Nobel Prize for that Bohr model, and it was a great achievement. And it somehow points to the subtlety and the difficulty in physics, where you can be doing something which clearly is in many respects inadequate, and yet is an important step on the road to the truth, which that model was. Of course, it can lead to wrong conclusions, as Tim said. Nonetheless, how does one tell in physics what kind of inadequate things is still something to be taken very seriously, and what kind of inadequate thing should be dismissed out of hand? It's not always an easy judgment.
Yeah.
So Tim described my list as lovely, but that list, it included the two of you, Barry, David, Nino Zangi, some other people, but you all agreed that the Copenhagen interpretation was unclear. And I'm wondering now, before we get to your divergences and intuitions, because, for instance, the two of you and David and Barry have very different approaches to and beliefs about the theories of quantum mechanics. But what was Bell, since you said he was the main person, was there one clear intuition or problem he had with Bohr's work that motivated him to try to move beyond it?
Yeah, it didn't make any sense to him.
Okay.
Really was. It really wasn't subtle. If you read Bohr, you just see how incoherent it is. The surprising thing is not that a smart guy like Bell couldn't stomach such nonsense. The surprising thing is that so many other people tolerated it. Smart people.
Yeah, I mean, you should also, I mean, ironically, Bell also says some nice things about Bohr at a certain point about the necessity of describing the experimental situation in, quote, classical terms, by which one doesn't mean classical dynamics, but it does mean essentially, macroscopic bodies with certain characteristics in normal space-time, right? That you sort of needed to be able to do that, which he appreciated that Bohr said that. But I mean, the thing that the two things that strike you about Bell are, first of all, he's just incredibly clear. I mean, you can't read anything he writes if you read it with attention and not really understand what he's saying. He's very sharp. And that's in contrast to trying to force your way through page after page of Bohr and just feeling at sea, like you don't know where you are, you don't know what's happening, you don't understand the structure of the arguments, you're just kind of, drowning. And I think one of the things that helped me was there's an appendix to one of the papers where Bell talks about Bohr's response to the EPR paper. And he just says, I can't understand it, right? I mean, I just can't follow what he's saying. And he gives quotes and says, I don't understand what this means. And that it makes you feel good, right? You think, oh, Bell is a really smart guy. If he couldn't follow this, then the fact that I can't follow it may not be a problem with me, right? It's a problem with the text.
Yeah, but
Gives
he
you
did
some
more than
courage,
say
right?
he couldn't understand it. He said he couldn't understand it, but then he gave a devastating critique of it.
That's true.
So I said a couple of minutes ago that you all agreed that the Copenhagen interpretation was insufficient, but the next part of David's story was that after sort of determining this and shelving it, you all ended up with completely different intuitions about which theory of quantum mechanics was in fact the correct one. And I would like to get more specifically to Bohmian mechanics in a little bit, which of course I talked with Shelley about, but I'm wondering if there is something before the adoption of Bohmian mechanics that you can identify as maybe there are multiple things that are the cruxes that resulted in all these diverging views.
Yeah, let me just correct, I think, the language. I don't
Please.
think correct is the right word there. Most promising, right? There are different approaches. We all understand none of them have been completed to the level they would have to be.
Okay.
And you have to make a decision, not which one is correct, but, which one seems to you, and there's a certain amount of subjectivity in this. Now, we've been through, I've got this kind of triage, which I think Shelley agrees with, that you either have to add additional variables, which you can do without disturbing the unitary Schrodinger evolution of the wave function. That's the kind of Bohmian route. You can put in objective collapses. That's the GRW route, or what Penrose is doing, or you're stuck with many worlds. It's got to be one of those three. And I think the only real difference between David and us was David thought that the objective collapse theories would allow you to derive everything you thought of as probabilistic, including thermodynamics and other places where probabilistic notions come in, from one theory. He used to say that, right? That it would unify in a certain way the probabilities that show up in quantum mechanics and the probabilistic reasoning that shows up in statistical mechanics and so on. And he thought that would be an interesting unification and simplification. I always found collapse theories, although I understand if you put the collapses in a rigorous way, you can try and make them work. They never felt right to me, right? This kind of dual dynamics never felt right to me. So I wasn't tempted in that direction in the same way. But again, I think I can appreciate other reasons for looking in other directions. Tell it, Shelley. I don't, how.
I agree with that. Yeah, here's the thing when you're working in, particularly, I guess, in foundations of quantum mechanics, you encounter all kinds of theories. Most of them don't make any sense at all, even though they get published. Then you say, okay, I'm not going to pay any attention to these that don't make any sense. Then you have some which sort of make some sense, and you say, well, how well do these theories do? And sometimes you find theories which do very well in explaining all the facts. They sort of make sense as theories, and then you try to judge between them. That's the way that's how the science should have proceeded. Nonetheless, it's not how it generally proceeds. Most practitioners, particularly physicists, I would say, tend to dismiss the theories that they're not proponents of without trying to understand them properly. Quite the opposite. They want to find reasons not to understand them. They use their great intelligence to find reasons to reject rather than to understand in situations where they should not be rejecting. This is all too common. It's aspect of human nature.
Tim, I hadn't heard the viable theories reduced to those three that you mentioned: hidden variables, GRW, and many. Well, maybe not GRW in particular, but
that's just a little that's an argument I gave many years ago in a little paper called Pre-Measurement Problems, and it's just. I thought we went over this. I don't know. I've done too many interviews. There are three propositions that are mutually incompatible. You can't hold all three. 1, the wave function is complete. 2, the wave function never collapses. And 3, experiments have unique outcomes of the kind you think, like the one cat you started with ends up either alive or dead. It's kind of easy to prove that you can't hold all 3 of those. And so then you can triage propose solutions by which one or ones. You could give up more than one, but mostly people want to keep all 3. So if you can give up one and get away with it, you tend to do that. Which of those 3 are you going to give up? I mean, this is the first question you should ask. If somebody says, I have an understanding of quantum phenomena, the first thing you should say is, well, do you believe the wave function is complete? Do you believe it always evolves by Schrodinger's equation or some linear equation? Are you a many worlds person, right? And if they answer no to all of those, then you know they're confused.
You probably know they're confused no matter how they answer it. I mean, because the way they answer is going to be all over the place. Confusion is par for the course. By the way, since three is a more complicated notion than 2, a corollary of Tim's observation is that if you insist, as many physicists would like to do, that the wave function must evolve according to Schrodinger's equation, then you have only 2 options. Either the wave function is everything, many worlds, or the wave function is not everything. There's other things. And that basically leads most naturally to Bohm. That's a very, very simple set of possibilities. And you would think that would be really clear. So I'm actually struck by the fact that so many people that I talk to, really intelligent people, who do want to say that the Schrodinger evolution is the fundamental evolution equation, but they don't. But they also insist they don't want to be Bohmian or have hidden variables, anything like that. But they say they can't make any sense of many worlds, and they wonder why would anybody believe in many worlds. This I find interesting. It just says the psychology is often more interesting than the physics.
Mm-hmm. Well, my psychology as somebody who's not a physicist, I think I fall into this camp, and my response is, how could anybody believe in many worlds because of how inflated this ontology is into a multiverse? But when I talked to Sean and David about this, they said that to them, this is a non-issue. The main concern is probability, making sense of probability.
Look, I think I would have to actually say their response there is fine. Look, this is in common between many worlds and pilot wave. You've got a wave function, you've got a quantum state, which is a physical thing described by this mathematical wave function. And it always evolves by Schrodinger's equation or some linear evolution. Okay, that alone, given how it evolves, is going to give rise to this tremendous, diversity of, and you can pretty much define what you mean by decoherence. It's going to give rise to this tremendous diversity of decoherent parts of the wave function, these things they call branches. You don't postulate them, as a separate postulate. That's just a consequence of allowing the Schrodinger evolution to just do what it does, right? So they're going to say, look, I haven't, what did I postulate? In fact, one thing they can say correctly is that their ontology is very sparse. It's only the wave function and only doing this very simple thing. So I don't think there's a kind of Occam's razor. I'm not very fond of Occam's razor at all in any case, but I don't think there's any Occam's razor criticism of many worlds. What I thought for a long time was the main problem was probability. What Shelley opened my eyes to is that there's a much deeper problem, and you also see this in Bell, and you can read Bell's paper, The Theory of Local Beables, which is if all you've got is the wave function, and the wave function is not a local kind of thing in space-time, and if all of our empirical evidence is stated in terms of the behavior of local things in space-time, there's a gap there you really need to fill, right? How does your theory bear on what we take the evidence to be? right? I mean, the language, and this is where Bell praises Bohr, of saying the experiment has to be described in classical language. That's local stuff in space-time. So if you don't know how to make a connection between your fundamental physical postulates and stuff going on kind of in a familiar way in a three-dimensional space-time at macroscopic scale, then you don't know how to connect your theory to what we take evidence to be. And that's a really bad problem. That doesn't mention probability. That's a much worse problem, a much more fundamental problem.
And Robinson, what Tim said is so simple and obvious that it's difficult to appreciate because it sort of sails under the radar. It's important to really digest that something so simple can be can be focused right at the issue.
Mm-hmm. Yeah, it seems like this is also a place where very basic concerns about ontology in the form of local variables really weigh heavily in what I will label the interpretation wars.
Mm-hmm. Absolutely.
Yeah. And is this then the basic crux of what motivates the two of you to adopt the model where there's not just a wave function, but a particle configuration, so that there are, in fact, these local variables?
Well, I mean, let me just say this again. I'm always just channeling things that Bell says, but I'll say it again. There's this term hidden variables that comes up, right? And Bell says that calling the particle positions in a pilot wave approach the hidden variables is a piece of historical silliness. And the other thing he says, which everybody agrees, is if you believe there's this quantum state, this wave function, this thing described by the wave function, it's really hidden. I mean, it's really hidden. If I hand you an electron and I tell you this electron is in a specific eigenstate of spin in some direction, some particular direction, I just prepared it so it's spin up in a specific direction in space, and I hand you the particle, and I say, do your worst, right? Do any experiment you want and try and figure out what quantum state it's in. What everybody will say is you can't do it. That cannot be determined empirically. That cannot be determined experimentally. The wave function cannot be seen in that sense. The only reason you have to believe there is a wave function at all and what it is because of the influence it has on things you can see, like where spots appear on screens. That you can see, but you cannot see quantum states. So if you start from there, the idea that, oh, I'm perfectly happy with there just being a quantum state and I don't want to mess it up by adding anything else, that just doesn't make any sense. Because the thing you're perfectly happy with is the thing that is hidden, right? It's not accessible. It's not directly accessible. And if you don't have anything else, then this is just another way of saying you're in a heap of trouble. Right?
I mean, you don't have to be at all original or do any kind of systematic analysis to say, in non-relativistic quantum mechanics for a system of particles, you're really dealing with particles, things with positions. The very language, the whole discussion in quantum mechanics seems to suggest that you've got particles. It's not that you have to be really clever and introduce hidden variables. You just say there exist the obvious things. Let's try that. It happens, that works perfectly. Why so few people tried it is a big mystery. You say the obvious thing. I really have particles, not just the wave function. I've got particles too. And they move in a way which is naturally suggested by Schrodinger's equation and the wave function. And out pops all the predictions, mystery, all the mysterious predictions of quantum mechanics, randomness and all.
I'm going to give voice here to a very naive question, but as a naive pre-theoretical person, I'm a good person maybe to voice it because I imagine other people have the same question. But so it's very important that there are these local variables. We're talking about particles. But these particles in quantum theory are point particles. They're zero-dimensional. And that goes very much against our experience of everyday objects. We can't really even... You don't think...
You have no experience of everyday objects at microscopic scale. That's why we call it microscopic.
Mm-hmm.
You have zero experience of how big a particle is, right? None. Nothing.
I think that I think that this is a perfectly good response to the objection. So my everyday experience cannot at all rule out the existence of zero-dimensional objects.
I mean, look, we often say if you for some weird psychological reason are very upset with point particles, fatten them up a little, right? Make them little spheres. I make them little statuettes of Mickey Mouse for all I care. It doesn't really matter.
That would be an interesting theory.
It would.
But to do that, suppose you rate for yourself, suppose you have this objection, this worry about, I have no experience of point particles. What a strange thing a point particle is. Then consider two theories, like Tim said, the point particle theory and then the Fatten theory. And then realize that the structure is such that the two theories explain everything in exactly the same way. Ask yourself, which theory will you then prefer? Should I complicate the theory just to satisfy my prejudice or not?
No, I think that's
I prefer the simplest theory, the simpler theory.
No, that's a very reasonable point. But I do think from my reading, and it's hard to remember where I get certain things, but it's often touted. This is really orthogonal to our discussion, but it's touted as a positive for string theory that we can abandon the point particle model, and we do in fact have these little I don't know how much better one-dimensional is, and then there are zero brains too.
Yeah, can I make a comment about that? I mean, I've heard Ed Witten several times. Maybe everybody has seen these Feynman diagrams, right? So you just have these diagrams. Look, here are two electrons, and then here's a little virtual photon that runs between them, and then the two electrons, it's kind of scattering, right? And one of the things that motivated Witten, and this is one of these places I understand the motivation. When you try to do quantum field theory using these diagrams, you have one piece of mathematics called the free propagator that takes care of the pieces of the diagram where there's no intersections, where the things are, as it were, just going straight, okay? But then you need to take care of the point in the diagram where three lines come together, right? Where there's an interaction, say, between the electron and the photon. And that requires entirely new principles, entirely new physics. You have to write down an interaction, and you can't derive that from the free propagator at all. And Witten didn't like that, okay? Now, if you turn these little point-like things into strings, into closed strings, kind of round loops, and you do the same diagram, it now looks like kind of a fat H, if you can picture it in your head, if you make all of them strings. And there are no points on the surface of that H that are fundamentally different than any other points. So his idea was, well, then a single propagator will work everywhere. And that's a cleaner theory, right? Rather than having the free propagator plus this other interaction term, somehow it's all bundled into this one thing. And that also made him think this would be a much more constrained theory, because in the first theory, I can give you the free propagator, but then there are all kinds of interaction terms you can throw on top of it. And in this theory, no, it's just one propagator. So from a kind of aesthetic mathematical point of view, I understood that, and that you would gain in string theory, at least at that level of understanding. I mean, that's the way he explained it. String theory doesn't work. There was never any reason to believe string theory, but that particular feature of it is one that you're helped by not having point particles. So that might be what they have in mind.
And something else they might have in mind, some of them certainly do have in mind, and let's say on a simpler level, quantum field theory somehow based with involving particles instead of strings suffers from, notoriously suffers from infinities. And the infinity has to do with how small zero size point particles are. And the idea is if you can spread them out a bit, for example, I'd make it a string. Instead, you're going to lessen the infinities. Things will get better. It could be that the arguments you've heard were based on those kinds of considerations. Those are reasonable considerations. They technically may or may not be correct. One has to see how string theory works, but they're reasonable considerations. The argument you first gave, a point particle is a strange thing, it's much better to have a string without based on any technical considerations, that's just sheer rhetoric.
Mm-hmm. I guess I'm kind of struck now, but I might have made a similar argument. Like my body can't be composed of cells. I've never seen anything like that. Way too small, way too complex. But point particles do seem a bit different. But I take your responses very seriously. They make sense to me. Returning though to our thread, I gather that one of the major philosophical or ontological problems with many worlds is that it doesn't have the local variables. And I'm wondering if there's a similar ontological problem to the spontaneous collapse theories or something basic like that. Or, I mean, as you put it, Timur, it just kind of makes you uneasy. You're uncomfortable with it.
So, two things about the collapse theory. One is just the collapses, okay? Especially if it's this trading off dynamics that a lot of the time it's Schrodinger and then all of a sudden it's something else. That's what you find in like von Neumann's book. And then if you associate the collapses with measurements, then you're in a complete mess, right? That's just a disaster. The GRW theory also has the original
before you go on, is it a complete disaster because then they're not spontaneous any longer?
It's a complete disaster because you don't know what a measurement is. Okay. This was the objection that Einstein said, can a mouse do it? An observation, can a mouse do it? What interaction counts as a measurement?
Should the notion of measurement play a fundamental role in the very formulation of a physical theory? I think most physicists nowadays would say absolutely not.
And that's the point. Again, go read Bell's Against, quote, measurement. He makes the point very, very, very sharply that the term measurement just should not appear in a fundamental theory because it's not a fundamental notion.
Mm-hmm.
It's like pianos. I mean, there are pianos, they exist, that's okay, but you shouldn't have to mention pianos or have to figure out whether a collection of atoms constitutes a piano in order to figure out how the laws of physics go, right? Mm-hmm. That's not on. If someone suggests that, you're just going to say, no, this is not on, right?
Oh, but then, Tim, maybe your idea of having electrons shaped like Mickey Mouse is not such a great idea.
Yeah. So there's that part. Now, I should mention that Philip Pearl has a kind of collapsy view, but it's not one with this alternation between Schrodinger and collapse. It's it's called a continuous collapse or a continuous reduction theory. Quite honestly, I see the pull of that, because if you don't like this alternating between this dynamics and that dynamics, okay, just have one dynamics. It is a fundamentally indeterministic dynamics, always operating in the same way. To me, that feels better. The other question you asked is, well, what about the local Beables? Now, this is a question that kind of got worked out in my living memory. Shelley and other people working with him clarified this. It was very helpful just to have a little piece of terminology. So there is a theory called GRW null with a little null sign in front of it. That means a theory where the ontology is just the wave function and it follows the GRW dynamics. That theory, I think, is in deep, deep trouble because it also has no local Beables, because all it has is the wave function. It's now a collapsy wave function, but it has nothing local in it. Then there's the theory that Bell himself suggested in his paper, Are There Quantum Jumps?, where he introduced this idea of flashes, the flash ontology. Flashes are physical events in space-time, points in space-time. If you didn't like point particles, you'll like this even worse. Points in space-time, they don't even persist, right? And what Bell did was he said, well, if I've got this GRW collapse theory with these sudden collapses, those collapses are centered at space-time points. So I can put those in. I have to postulate them. They don't come for free. I can postulate that there are these physical events in space-time that happen when these collapses occur. And they're distributed in space-time. And if you kind of squint at them, there are enough of them that you'll see tables and chairs and cats and planets and stars and everything else at macroscopic scale outlined by this collection of flashes. So then that doesn't have the problem. Then Giancarlo Girardi didn't like that too much. So then they tried to come up with another theory, which was the GRW dynamics with a matter density ontology. So it doesn't have this discrete flashy character. It's more like a continuous field that you define down. And that behaves in a different way and has different issues with it. So I would say GRW null, yeah, that's as bad as many worlds. GRWF, it has some technical nice advantages. GRWM, some of the advantages go away. Bell liked GRWF for various reasons that he gives in the paper, because he thought you could make it into a relativistic theory.
The M, when Tim said this, the M, that's an M, that's a field on physical space, not on the space in which the wave function lives. It's crucial here that it's projected down to physical space. This primitive on top, the local beables are normal local beables on physical space. That's the M, the mass density, distributed over physical space.
Well, I think that this is probably a good time to make our jump to talking about Bohmian mechanics more particularly. But one thing you said about the collapse options is one of them involved a fundamentally indeterministic dynamics. And when I was talking to Shelley, I think at one point Shelley asked me what I thought the crucial innovation of Bohmian mechanics was. I think I am now not recalling if Shelley, if you thought I was wrong, but I said that there is this dual ontology of particles and waves. But one other thing that I might have said was that and I guess this isn't isolated to Bohmian mechanics, but this is very important, I think, is that it's deterministic. And one my zero-dimensional objection, which you handily waved away, there's also an objection to a lot of the interpretations or quantum mechanical theories that they're indeterministic. And I'm wondering if that doesn't make either of you feel queasy and point you in the way of deterministic options like Bohmian mechanics.
I guess I would feel that I don't have a strong feeling about the importance of having determinism, but I can appreciate that somebody might. So right now I'm in the state where if I have two theories in front of me and one of them is much simpler but non-deterministic and the other is more complicated but deterministic, I'll prefer the simpler one.
Yeah, I would entirely agree with that. I don't think the determinism-indeterminism issue is of zero importance. If I had two theories that were tied on every other metric, but one was deterministic and one was indeterministic, I'd go for the deterministic one, right? But they're never really tied. When Bell, Bell really was a big advocate of the pilot wave theory. When he tried to then do a pilot wave kind of treatment of quantum field theory, he did something that lots of physicists do. You take it out of a continuum, you put it on a lattice. So instead of having things defined in a continuum like a Euclidean space, you put it on a discrete lattice. And if you do it on a lattice, it's almost the only thing you can do is have an indeterministic dynamics. At least that's the most natural thing to do. So that's what he did. It's all in the spirit of pilot wave But if you happen to make that move to go to discreteness in the space-time structure, the natural thing to do is to make it indeterministic. The other thing that happens, just one other piece of actual stuff that happens in the world, is particle creation and annihilation, right? So this is not covered in quantum mechanics. It has to be covered because it happens. If you think that this is really creation and annihilation, that these are new particles coming out of where there weren't any before, it seems like the most natural way to do that may be indeterministic. Of course, the Dirac-C picture was that, no, that's not what's happening. You're lifting a negative energy electron, which is there all along, up into positive energy space. So nothing's really coming in. And you could imagine that being deterministic, right? It being popped out somehow, if you will. So you got a lot of decisions to make about how you're going to approach these issues. And in some of them, probably indeterminism is pretty much the only reasonable way to go. And in others, it may not be.
And even if you don't go to a lattice in discrete space, but stick with conventional, continuous, smooth, continuous, normal physical space, and try to understand in a Bohmian sort of way, that is, in terms of a primitive ontology of particles for quantum field theory, you're naturally led, when you consider the interactions, to a stochastic theory.
Well, as we talk more about Bohmian mechanics, it's been a little while since Shelley's episode, and Shelley explained Bohmian mechanics, but maybe, Tim, you could give like the brief elevator pitch just to remind our listeners of what it is and what you take the crucial points to be.
Well, I'll just say, and I'm going to kind of just channel what I learned from Shelley, maybe say something a little differently than he does that helped me. Everybody learns Newtonian mechanics at some point. It feels like they understand it. And usually with point particles, right? You treat even the Earth as a point or the sun as a point because it's easier to calculate, right? There are arguments why that's a pretty good approximation, but you're used to thinking of these particles moving around. And in Newtonian mechanics, the state of a system at a moment is given by the positions of these particles and their velocities or their momenta at that moment, right? And then you have Newton's equations, and that tells you the forces, and that tells you how the momenta change, and the momenta tell you how the particles move, and everything. You kind of see what's going on, right? So here's a thought. Get rid of the momenta. Just, you have still particles, they still have positions. It's not it's a theory in which the particles' motions are now determined or guided by something else. And this something else is the wave function or the quantum state, this thing that's described by this wave function and Schrodinger's equation, and that's just common coin to every version of quantum theory. Everybody's got that. And you say, well, what's its role? What's it doing? Well, in this theory, it's guiding the particles. It's guiding the particle configurations. It's determining how they evolve. And then you say, oh, well, how does it do that? You've already got the wave function. You already got Schrodinger's equation that you can pick out of any book. You need an equation for that. And so there's an equation called the guidance equation. And it turns out, in the case of quantum mechanics, to be an unbelievably simple equation that, I don't know, Shelley says, I don't know, there are a dozen different ways you might arrive at it by heuristics. So you plug that in and it works. Gives you all the right predictions. I think you should be pretty impressed by that.
Okay.
Yeah, twofold impressed. Number one, because it's so nice that such a simple thing works, but that's with the background that almost the entire physics community had insisted that nothing remotely like that could possibly work. No hidden variables whatsoever could possibly explain quantum phenomena, quantum randomness, anything. Couldn't work. And now it turns out the most obvious thing in the world works. You're talking about a system of particles, so take it seriously. You've got particles, things with positions. Ask yourselves, how should they move? Let's make the obvious guess. You make the obvious educated guess. You got the theory, the wave function, particles moving in a certain way. Your natural thought would be at this point, okay, that theory can't possibly work. Because if something so simple worked, everybody would have accepted it. Nobody would have been talking about the impossibility of any such thing. Nobody would be talking about all this craziness, all this incomprehensible craziness. So, of course, that theory can't work. You analyze it and you find it works perfectly. Everything is explained. All the phenomena of non-relativistic quantum mechanics are explained in a completely comprehensible way.
And Tim, you said that the wave function determines the way that the particle configurations evolve. Mm-hmm. And I'm wondering, for our lay listeners, for me, how you visualize this happening. Is it something like, on a microscopic scale, a surfer being pushed by a water wave? Or
okay, yeah. So this is the thing that people say, right? People who don't like the theory say, oh, it's a cork being pushed around by a wave. The problem with that is that a cork is, for the purposes of that analogy, is a single point particle, and all it does is move somewhere or other in the ocean. What we're talking about being guided here is the configuration of all the particles. So unlike a point, that configuration already has a tremendous amount of structure, right? The configuration of, Avogadro's number, right? 10 to the 23rd particles. If I just give you that configuration, I can tell, is it a cat or is it a dog? Is it a sofa? Okay. If there's, to use one of Einstein's examples, if there's a keg of gunpowder, did it explode or not? Okay. If this keg of gunpowder has all those particles in it, and I give you just for a single instant its configuration, you can very easily tell whether it exploded or not, right? If it exploded, the configuration is the particles spread all over Kingdom Come. And if it didn't, the configuration is all the particles packed together in a keg. That's with no dynamical information, with nothing going through time, with no considerations about counterfactuals, with no considerations about anything. Just the configuration of many particles has already a very important structure that makes this thing interpretable. So if you think that entire configuration you're thinking of as just a cork and all it's doing is bobbing, then you're going to be very puzzled. You're going to say, well, wait, how does the cork have to bob in order for me to break my leg? How does the cork have to bob in order for a needle on a meter to go this way rather than that way, or to a spot to form on this part of the screen rather than that part of the screen? You'll be very puzzled about that. But if you see, no, it's not a cork. It's a configuration of as many particles as you like. And that contains, those are the local beables, and that contains a tremendous amount of information about what's going on, just even at an instant. That's why it's entirely misleading to think of it as a point. And that's why, I mentioned to you the many worlds people who say, oh, this Deutsch nonsense about how Bohm is just many worlds in a state of denial. Why? Well, you've got a wave function. It never collapses. So you've got all these branches. And then Deutsch says, look, there are these many worlds. And then you want to say, no, because there aren't any worlds that I can recognize because you don't have any local beables. When I add the local beables, I add a whole lot of them. I don't add a single point. And its purpose is not to indicate a branch of the wave function, which is what they say, right? Its point is to be the world we're familiar with cats and dogs and chairs and tables and people and meters, right? And laboratories and people doing experiments. All of that's in the particle configuration, or it can be recognized in the particle configuration. So that's why this picture of a cork bobbing along will really take you the wrong direction. It's the entire configuration changing, right? That is what the wave function is coordinating or choreographing.
But let me say something else about your question. You're really asking, okay, how can we understand why the particles should move this particular way? And often people want to have, oh, it's like this, oh, it's like that, oh, it's just like, Bohm talked about particles being like a little radio receiving information somehow from the wave function or whatever. These things, they may help some people, but they are entirely misleading. You have to ask yourself, how does a fundamental physical theory work? If you say, oh, the way it works is I have to appeal to a deeper theory to explain what's going on, then it wasn't the fundamental theory. If it's a fundamental theory, your questions have to stop somewhere. If you have compelling mathematics describing how the local beables evolve, and then you're going to say, oh, but that's not good enough. Even though it's compelling, it's simple. But why should it be that way? And you want to say, oh, I have to understand that in terms of something more familiar. Why should you expect that? This is the fundamental theory. What more do you want than having a theory involving simple structures evolving according to simple laws of motion? Why should you have to derive those laws of motion from something else?
Right. Feynman made this point in a very nice interview. Maybe you've seen it, where somebody's asking, well, can you really explain, for example, why there's an electrical attraction between a positively charged and a negatively charged particle? Can you explain that? And he said, well, I could kind of try to give you a model in terms of rubber bands or something, which might make you feel better. But he said, but that's a cheat, because the way rubber bands work depends upon electromagnetic theory. I mean, you've got the whole thing upside down. I'm appealing to the fundamental electromagnetic theory to explain rubber bands, so I better not be putting rubber bands into my understanding of the fundamental electromagnetic theory. I mean, explanation has to come to an end somewhere. My dissertation advisor, Clark Gleamore, in his book says more or less the same thing. He says, look, sometimes when something happens, there's like a Rube Goldberg device, right? You know, why does the kettle get taken off the stove while there's a man walking along and he slips on a banana peel and he falls and he pulls this and this happens and that happens? And he says, but that can't go on forever. You can't say, well, but why is the banana peel slippery? Well, now you put another Rube Goldberg device to do that, and then yet another one to explain all the mechanisms of that. That's just a mug's game, right? That's just silly. Where do you end in your explanation? You end somewhere simple. You end somewhere where it feels like this would be a good place to give up asking for further explanations, right? And that's just simplicity and clearness and things like that. So, you know, you shouldn't, what more could you expect? If you expect more than that, and certainly if you expect an understanding in terms of your everyday experience, that's just silly. Why should your everyday experience be a good guide to how quantum states make configurations, you know, direct configurations?
Okay, you've given me enough ammunition for quite a few questions, and let's see where I should even start. Maybe I should start with the quark metaphor, and I think that the quark metaphor probably arises from popular physics. Well, maybe I have no idea where it arises actually, but I know where it arises for people like me is in popular physics books that describe Bohmian mechanics, usually in the context of something like the twin slit experiment. You get an image of a wave guiding an electron, like it's a surfer on a wave. And I'm wondering, yes.
Yes, can I make a comment about that?
Please.
A single particle system, which is what you're looking at there, a single particle, you have this very, very, very special situation that the configuration of a single particle, the configuration space of a single particle is physical space. That is, you specify what we would call the configuration of a single particle simply by telling me where it is. So the wave function, which is defined on configuration space, for a single particle and only for a single particle, can be pictured as a field on physical space, like a water wave. But once you get up to two particles, nope. Because the configuration space for two particles is 6-dimensional, and the configuration space for three particles is 9-dimensional. And the configuration space for 6 times 10 to the 23rd particles is a hell of a lot bigger than physical space. So it's okay to think of the two-slit experiment for a single particle in that way, as long as you're aware that it is a very, 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 very special situation, which would be extremely misleading if you thought it generalized beyond a single particle in that way. That once you get to more than one particle, the wave function is not defined on physical space. You can't picture it as something on physical space. It doesn't have values in physical space, and so on. Does that help? I mean,
no, that helps quickly, because obviously, I mean, we can't envision 4-dimensional object. I mean, it's well documented psychologically. I think that people can't envision a hypersphere or a hypercube or something like that. So clearly, we're not going to be able to come up with a good visual metaphor for something that's 6-dimensional, or God forbid, much bigger than that. So no,
that's something Kim just said. If you want to understand the nature of the wave function, you better be thinking about more than a wave function for a single particle, because you're going to get entirely the wrong idea if that's what you focus on. The essential innovation that is the wave function arises when you consider the wave function for more than one particle.
And then, Shelley, you said some very interesting things about Bohmian mechanics of the fundamental theory that I want to get back to in one moment, because I wanted to first finish up Tim's handling of the criticism leveled by David Deutsch and the Oxford people in defense of many worlds, where, if I'm correct in recalling what you just said, they sort of labeled Bohmian mechanics as many worlds plus a particle configuration. And did you also say that Bell had already, you might have said this in an email to me, that Bell had already addressed this earlier on?
I'm not sure.
Just what?
Bell didn't spend a lot of time on many worlds. The only many worlds theory he could understand was not the standard one with splitting. He came up with what's called Bell's many worlds, where you always have a single particle configuration, but it jumps around at random. At every moment, it kind of jumps around in accordance with the square of the wave function. That's not the one that the Everettians have in mind. I don't know if Bell ever talked about the kind of splitting and stuff like that happens.
Well, Bell was well aware of it, but that was all too vague. In trying to get to the heart of what he took to be Everett's proposal, he first demanded a clear ontology for the worlds. And that was a particle ontology. Anything, because Bell demanded a clear ontology. And then he somehow realized that insofar as the theory explains anything, he doesn't need all the worlds. One would be sufficient. So he threw out all the rest, which makes it a very eccentric version of Everett. He calls it Everett with a question mark. And then in exploring the details of his version of Everett, which he thought was ridiculous, he points out how ridiculous it is. It leads you to a complete reduction ad absurdum. If you believe his theory, you can't believe anything.
Right.
Yes, he points out.
Not many people are going to follow it, but I just have to say it because it may be lost. I don't know if it's printed anywhere. Bell gave a talk at the PSA meetings back in the 80s. And in that talk, he talked a little bit about part of what was going on in many worlds, which was decoherence. I'm sure you've had people bring up decoherence. Okay. So kind of a picture in your head is if you had a big matrix that's representing the wave function, if it decoheres, then the only entries are down the diagonal, and all the off-diagonal elements have somehow gone to zero. All right. So this is just a kind of picture in your head of what you're looking for decoherence. And Bell made a wonderful comment, because this was when so-called environmental decoherence was becoming very, very fashionable. And he said, well, it's true that if you pick any of those off-diagonal elements and wait long enough, it will get as small as you like. But he said, but it's also true that no matter how long you wait, there'll be some off-diagonal element that it is as big as you don't like. So he thought that all of these arguments were really, again, just logically flawed, who were people who were looking at decoherence as somehow magically solving these problems. But it was a wonderful, this is just Bell again, kind of making this wonderful comment.
Well, okay, without further ado, then getting back to Shelley's comment about fundamental theories, that I will just ask why you label Bohmian mechanics as a fundamental theory when, as far as I'm aware, it, and my awareness doesn't stretch that far, it's not a theory of quantum gravity, at least at this point.
It's not a fundamental theory in that sense. What a more accurate statement would have been let's say, in some sense, a potentially fundamental theory. You want to understand the theory, pretend that it's fundamental and see what the world will be like if this were the fundamental theory. Stop worrying about where the theory comes from or what the deeper theory from which this theory might emerge is. You want to understand this theory, treat it as if it's fundamental.
But what features of pilot wave theory make it promising to you as the potential fundamental theory?
No. It's not let's say the world is quantum mechanical, which I think, I'm not sure how many people actually believe that ultimately the world will be found regarded as quantum mechanical, but I think I'm naive enough to say, okay, maybe it is so. Maybe the world is. I have a feeling in 1,000 years we're going to say that all of this quantum stuff is nonsense. But right now I'm naive, and I think the world should be quantum mechanical. All the evidence suggests quantum mechanics is the way to go. Some version of quantum mechanics. So what does that mean to have a theory to be a version of quantum mechanics? I certainly don't want any Copenhagen-ish theory. I want something coherent, where I know what the theory is really about. And it's definitely not fundamentally about measurement and observation. If somebody gives me a theory and the axioms involve measurement and observation, and they tell me it's about measurement and observation, I can stop listening. I know it's not a serious theory. Now, so I've got the wave function, and it involves according to something like Schrodinger's equation, and Schrodinger's type equation. Fine. And there has to be more than the wave function, unless you go to the many worlds route, which I think is a big mistake. So it's not hard to say there's more than the wave function, because if you have more than the wave function is given something to do. It's not everything. It's simply giving. It's sort of an object of the kind we standardly introduce into theories to play a role in the behavior of something we already have, like the electromagnetic field. It plays a role in the behavior of charged particles. Wave function definitely plays a role. It's orthodox quantum theory, the role the wave function plays. It's not many worlds orthodox quantum theory. The role the wave function plays in orthodox quantum theory is on the level of measurement. That's entirely the wrong level to assign a role to the wave function. And when you try to do it that way, you make a really complicated mess with a whole slew of axioms, measurement axioms. If you assign a role to the wave function on the level of the particles, on the microscopic level, it's very easy to do, and you just need one equation, the guiding equation. So that all makes good sense. Now suppose we come to a more fundamental theory, quantum field theory, quantum gravity, whatever. Then if it's a quantum theory, there should be a wave function playing a similar role, governing the behavior of the fundamental objects of the theory, which will not be the wave function. That's what I would consider to be a sensible fundamental quantum theory.
I'm wondering if this wasn't a crucial part of your response, Shelley, but I'm wondering if we've found a place where you two diverge, and it's your hunch that in 1,000 years people might have gotten rid of quantum mechanics. And I have a feeling that Tim won't feel that way. Am I off the mark?
I think we get into a semantic issue here.
Okay.
I mean, look, what does history tell us? History tells us some theories that were really impressively empirically successful turned out from present perspective to have been fundamentally wrong. Just fundamentally wrong, right? Newtonian mechanics seems to have been fundamentally wrong. Newtonian gravitational theory seems to have been fundamentally wrong. Certainly, if you believe in general relativity, you're going to say it wasn't just in detail that Newton's gravitational theory was wrong. It's in, if you think that what we call gravitational phenomena are a consequence of the curvature of space-time, then Newton was just way off base. I mean, he was completely off base, right? But nonetheless, that theory makes really good predictions. I mean, at NASA, they still use that to pilot their landers to land on Mars. They know that theoretically general relativity would make slightly better predictions, but at the level of accuracy they need, they don't care. So one thing we know is that the mere empirical success of a theory at a certain time is no guarantee that it's even, as it were, in the right ballpark at a fundamental level. Could there be huge shifts in the next 1,000 years? Of course there could. Would those shifts, I mean, part of the problem or part of the advantage that quantum theory has at the moment is that unlike Newtonian mechanics, nobody knows exactly what it is. So it would be a little easier for the word quantum theory to be inherited by the successor, right? Because you're not quite sure what quantum theory is anyway. So, I mean, there's part of this is just a semantic issue. Will they still call it quantum theory? How close will it be to what we have now? No, I don't really disagree. I don't know. Certainly, because quantum theory is the best thing we have now, the way to spend your time, unless you want to go really take a flyer and go off in some entirely new direction and cross your fingers that you'll get something empirically successful, is to think about that theory and kind of make incremental progress from it as a base insofar as you can. I think that's the best heuristic advice anybody could give you at the moment.
Yes, I suppose that even though quantum field theory has been empirically confirmed to like 14 decimal places, the 31st decimal place 1,000 years from now, they might get a major discrepancy that tosses everything on its head.
But it's not just that. Again, the theories can turn out to be conceptually wrong, but empirically right. Right? And so I'm not talking about the failure of the empirics. You might have as it were, a theory that doesn't correct the predictions of quantum field theory, but derives them in a way and from physical postulates that are much clearer and maybe even mathematically more tractable, right? You don't get all kinds of infinities. You don't have renormalization problems. There are various conceptual problems that might go away. It wouldn't necessarily mean that the theory as it is now fails empirically, but it still might be replaced by something that just seems much more satisfactory.
Yeah, that makes sense. Shifting gears again, in an email you mentioned that you and Shelley are both working on something called emergent relativity and in different directions or from different directions. So what is emergent relativity? And then maybe I'll just hear from both of you the ways you're tackling this problem.
Well, all I mean is that I'm thinking of relativity, special and general relativity, in the normal way as theories of space-time structure. Special relativity just says the space-time structure is Minkowskian, so it has a light cone structure. There's, a bunch of stuff that's well-defined. If you write down your fundamental equations of physics, the space-time part that goes into it should be Minkowski space-time for a special relativistic theory, and only Minkowski space-time, nothing else. In general relativity, you then add curvature to that, but it's kind of the same deal. You now need an equation to explain the curvature, but then you write down all the rest of your theory just in terms of the space-time structure of this curved four-dimensional manifold. Well, you can take that to be fundamental and absolutely correct, right? That fundamentally space-time has the structure postulated by special or general relativity. And you can take that as a constraint. Or you can think, no, maybe at a deeper level, at a more fundamental level, it's not like that at all, okay? In particular, in relativity, there is no preferred foliation. There's no slicing up of this space-time into, as it were, successive moments of time, the way Newton had. That seems to be something we need because of the non-locality, the violations of locality that we see in the lab by violations of Bell's inequality. My feeling is, okay, put it back in, right? Einstein
put a preferred foliation back in.
Preferred foliation. Einstein had good reason to get rid of it because he didn't need it. But he didn't need it because he was trying to recover theories, namely Maxwellian electrodynamics and Newtonian gravity, that couldn't violate Bell's inequalities. He didn't know that they were violated. He didn't know what they were. Okay, now we know what they are. We know they're violated. We know that no local theory can work. The easiest way to write down non-local theories in a clear mathematical formalism is to have a preferred foliation.
Let me make a comment here. If preferred foliation sounds like sort of an arbitrary thing only from the point of view of relativity, from the point of view of conceptual structure of space and its relation to time before relativity, it would be silly to... Preferred foliation would be a very strange way to talk about the situation in which what's fundamental is stuff spread over three-dimensional space, and that changes with time.
Right.
Right.
Yeah, I was going to add, that's exactly what I was thinking. I know that, Tim, you have a very different belief about time from, say, David Albert and Barry Lower. You take time as being fundamental. And because of this, is that something that leads you to desire a preferred foliation?
No. There are several different issues here. The ones with Barry and David, let's just leave aside because they're good issues, but they're a different discussion. This one is just, do you want to say at a fundamental level, there is this slicing, as it were? Physicists are extremely, extremely conservatively, sometimes rabidly opposed to such a suggestion, right? They'll say, oh, that's going back to Newton or something, although it isn't. And then you say, well, I do have a reason for wanting to do this, namely non-locality, okay? And the fact, as Shelley says, the wave function is defined on configuration space. The notion of a configuration depends upon where are all the particles at a moment, right? That's what a configuration is. So then the next question is, well, gee, but if there's this preferred slicing, why does relativity work so well? Because it sure does work well. And there are lots of predictions that you get out of relativistic considerations that turn out to be accurate. Then I think you want this idea, well, yeah, I want relativity to emerge in exactly the same way that we want something like Newtonian mechanics to emerge. We want something like Newtonian gravity to emerge from general relativity, even though it's fundamentally different conceptually. Why? Because Newtonian gravity works really well empirically. It better emerge in that sense.
Yeah.
We want something like Newtonian mechanics to emerge. We want something like Maxwellian electrodynamics to emerge from quantum electrodynamics. Why? Because it's a pretty good theory. You know, it's not exactly right, but it makes lots of good predictions. You better have a compelling reason to believe that in a certain regime, those predictions ought to be pretty near on target. So I think you want similarly an understanding of why, if space-time isn't fundamentally relativistic, nonetheless relativistic structure emerges from it. So it's not such a surprise that various heuristics worked. I mean, that's what I'm working on. I think that's the right way to go.
Is that the same motivation for why you're working on it, Shelley?
What Tim said, I agree with everything Tim said. Now, I suppose the way to implement that, Tim and I are working in probably different directions in the implementation, but in the description of the kind of project that Tim described, yeah, I totally agree. Well, I'm working on this with Nino Zangi. Been working with him on this sort of question issue for many years, and we make extremely slow progress. Part of the reason we make such slow progress is we're mathematically incompetent in the subject matter, because the mathematics is way beyond our expertise. That's one problem. The other problem is we work on this stuff when we meet every 6 months, and once we meet again after 6 months, we've forgotten almost everything we had discussed the last time. So we almost have to start from scratch again. That really does slow down the work. But this is true, and I've told Nino, and you should say, why don't you take the notes? I tell Nino, take notes on it so we don't have to start from scratch, and it never seems to work out for some reason. So we always have to start from scratch again. Anyway, it's fun, but it is a bit frustrating when we realize, what the hell did we say 6 months ago? And it's not. Tim is young; he can still remember things like that. Nino and I have trouble remembering what we were doing, what we thoughts we'd had 6 months ago on the subject. Some of them were tricky thoughts too. But something that plays a role, we've been focusing on something called geometrodynamics, which means an evolution, a natural evolution, some kind of natural evolution for three-dimensional geometries changing. Let me say changing in time, to use the conventional term. Now, what plays a crucial, there's a natural way of going from an evolving 3 geometry to a 4 geometry. There are, in fact, many natural ways, many ways of doing it. These different ways of doing it correspond to what you could call different gauges. What plays an important role in our thinking is the huge gauge symmetry, which you have at your disposal. It could turn out that when you exploit the gauge symmetry, there's going to be a gauge which leads you to a kind of structure, which is a very convenient structure, because in terms of this gauge, you have much more symmetry than you thought you had as a gauge choice. And that symmetry which arises as a gauge choice could be the Lorentz symmetry of special relativity. Now, we're very far from any success in this direction. But it's too difficult for us mathematically. But it seems to me, if we had the mathematical ability, it would be quite promising.
I'm just going to add, this is going to be incomprehensible to all but very few people, but to understand why we're going in different directions, I'm not aiming for Lorentz gauge. I'm aiming for Coulomb gauge.
Oh, I wasn't, but I didn't mean Lorentz gauge. I mean Lorentz symmetry.
Yeah. Okay.
Tim, are you working on the mathematics of this, or are you working on the philosophical?
I'm working on the mathematics of what I'm doing, because I made up the mathematics of what I'm doing. I'm doing something, I'm working on ways of thinking that space-time could fundamentally be discrete, and not a continuum at all. And
is that something that you have an intuition about?
Well, I have the intuition that it hasn't been studied enough, right? Already Zeno understood it could go either way, right? And he has paradoxes for continua and paradoxes for discrete. Many physicists say, with not much to back it up, that, of course it'll be discrete because at Planck scale, blah, blah, blah. But there's no, as far as I can tell, there's no good arguments there. And then they say it's all foamy and kind of, chaotic. I don't know. Mine isn't foamy and chaotic at all. It's very simple, discrete little structures. If you do it the way I'm doing it, you're just going to have a foliation built into it. You can't do anything like what I'm doing and avoid there being a preferred foliation. So that's coming for free. About the only way to do something discrete that doesn't really have one is more like what Faye Dowker and Raphael Sorkin do, this causal set stuff. That's also discrete, but they do it in a way that's supposed to maintain Lorentz symmetry at a fundamental level. I break that symmetry at a fundamental level. That's why I wanted to emerge at an emergent level, right? So that it's not a mystery why relativity works so well. But as far as I know, Shelley's not trying to do anything discrete at all. I mean, the shape dynamics he's doing is all continuous, and so we're doing very different things.
But of course,
mathematics of what I'm doing is really simple, because I make the bug a feature, right? I'm not a good mathematician, so I can only do really simple.
Maybe we should switch to discrete, because then we can handle the mathematics. No, I have nothing against discrete. Some people find that's perfectly. It's certainly something important to explore. No reason why that couldn't be right. We don't know what's right.
Well, maybe for these last 15 minutes or so, we should switch back to some bigger questions. And what I have in mind is I really enjoyed at the third of the way through our conversation, Mark, where we were talking about many worlds, the ontological problems there, and then some of the issues with spontaneous collapse theories as well. And I'm wondering, you two are very much devotees of the pilot wave theory. What are the best criticisms that preclude very smart people like Barry or Sean or David from jumping ship and joining you two?
Well, what
now we're into psychotherapy.
Were their favorite versions of quantum mechanics?
I don't think I've asked them,
because I'm not sure Barry or David would say that they prefer one thing over. They both are fans, I think, of Bohmian mechanics in one version or another, and of spontaneous collapse theories. Neither of them like many worlds.
Yeah. Mm-hmm. And again, I mean, there was a time, I'm not sure if he's still doing it, to tell you the truth, but there was a time when David, for the reasons I gave you, thought, gosh, I've got probabilities coming up in statistical mechanics. I have probabilities coming up in quantum mechanics. If I go with a collapse theory where you have these probabilities built in at the fundamental level of the dynamics in these collapses, then I only need to bring in probability once. Okay, I mean, that was an argument at least he used to make 20, 30 years ago. And I can see some appeal to that. I myself feel like I understand statistical explanation and what goes on in statistical mechanics in a way that doesn't require a probability measure, that requires notions of what are called typicality. I learned, again, a lot of this stuff from Shelley. So I don't feel like I even want a single notion of probability to take care of both quantum mechanics and statistical mechanics. I think that there's a way of understanding the nature of statistical explanation where you'll get confused if you think you need a probability measure for that. But that's a consideration. But I don't know. They would have to explain why they don't like it. I feel uncomfortable trying to explain why they don't like it.
Sure. I think I agree with you, David. David mentions GRW a lot. I think it came up when we talked last week. So I have the sense that that's his preferred theory.
To ask him whether it's simply something he's been working on a lot, or whether it's genuinely preferred. It's not clear to me what he prefers.
I was just using them sort of as placeholders since they're familiar names, but I meant just more generally, the criticism of David Deutsch aside, are there any glaring issues with Bohmian mechanics or perceived glaring issues?
Look, the kind of thing that David Wallace will say is, well, but there's no Bohmian quantum field theory yet, or whatever. And I mean, it's true. It's also true that standard quantum field theory, not even Everettian, is, a mathematical mess. It has all kinds of issues. It's not like it's some pristine, clean theory. that you understand. I mean, there seems to be a lot of double standards here. What can I say? There are people who will, they'll point out whatever it is, the mote in your eye, and miss the beam in theirs. I mean, there are a lot of these criticisms that don't stand up if you just apply them both directions. I think some of the rhetoric annoys me. David Wallace will say, we should believe in many worlds because the sky is blue. And that's just silly. I mean,
does he actually say that?
Yes. He has a paper giving talks with exactly that title.
What's the motivation?
Well, the blueness of the sky is explained by quantum field theory, but there is no Bohmian quantum field theory. But there's no Everettian. I mean, nobody's ever done anything from beginning to end using Everett, ever. There's this rhetoric as if what's done in standard physics is Everett. It isn't. What's done in standard physics is incoherent, right? It's the air of Copenhagen. It's incoherent. It has collapses. It has these measurement postulates. It has these algebra of observables, all the stuff that everybody's trying to get rid of because it doesn't look fundamental. Everettians want to get rid of it too. The idea that what has been done in physics is Everett is just not correct. So that rhetoric and Deutsch's rhetoric, as if they can't understand that the configuration is not a structuralist point, right? The configuration has a heck of a lot of structure. And they say things like, the only point of the configuration, let me just say one last thing. They say, the only point of having a single configuration, like in Bohm, is to indicate a branch of the wave function. It's like a pointer. It says, this branch, and then you analyze the branch to figure out what the world is like. And that's just such a complete and total misunderstanding of the theory that it's hard to understand. And here's an easy way to see it. Suppose I have a meter with a pointer on it, right? If you only have the pointer and not the gauge, the pointer pointing one way or another doesn't mean anything, right? And if you only have the gauge without the pointer, the gauge by itself doesn't mean anything, right? You only get significance by having the pointer pointing somewhere on the gauge. But if you just give me the single particle configuration at a certain time in Bohmian mechanics, say you're going to do a kind of Schrodinger cat thing or do Einstein's where either a keg of gunpowder is going to explode or not, and you just give me the configuration after the end of the experiment, you don't tell me the wave function. You give me no information about the wave function. So the configuration isn't pointing to a branch on the wave function. You just give me the configuration. I'll tell you whether that keg of gunpowder exploded or not. As I said, because if it did, the configuration will be a bunch of particles spread out all over everywhere. And if it didn't explode, it'll be a bunch of particles all packed together in the same location. That's not a pointer. I mean, they're so much think that all the work is done by the wave function that they just can't understand that in this theory, it's not. And I mean, maybe they don't like the theory, okay, but you shouldn't misrepresent it. That's what annoys me. There's some of these criticisms that are so far from being accurate that I can't understand why they're even repeated anymore, except for pure rhetorical purposes, which, that's not the right way to proceed. Right?
And it's not that there aren't versions of Bohmian mechanics, Bohmian versions of quantum field theory. None of them are definitive. There are a variety of different versions. None of them definitive in the sense that quantum field theory is not definitive. There are problems which remain. But it's hard to see which step for a Bohm, which direction for a Bohmian quantum field theory is the right direction. But the surprising thing, the lesson one should have learned, is not that, the fundamental ontology of the theory must be a particle ontology. What one should have learned from Bohmian mechanics and non-relativistic quantum mechanics is actually how, contrary to what everybody was saying, how easy it is in the case of non-relativistic quantum mechanics to add to the wave function actually something pretty obvious, which will do the job and get rid of all the conceptual muddle. Now, that it should be so easy in the case of quantum field theory is not something one should expect. That it should be possible, then it better be possible. Otherwise, I don't believe that quantum field theory can be made sense of physics. There has to be more than the wave function. And if you ask, well, why hasn't somebody found something definitive? The answer is very simple. Not enough people are trying. What you should ask, how do I incorporate the mathematical structure that you have with quantum field theory into a larger picture, which has coherent, well-defined local beables, which produces a satisfying whole? That's the question. Very few people are actually working on that in a hard way.
Well, this points the way to the question that I wanted to end with, which is how it is going forward you intend to convince the world, and maybe this isn't something that you care particularly that much about, but that Bohmian mechanics is the most promising quantum mechanical theory. And I'm guessing that it involves both philosophical argumentation and then development of the mathematics and physics. But is there anything more particular than that comes to mind?
I'll let Tim answer the question, but let me just say I think it's much more important to convince the American people that having Trump as president again is not a good idea.
It's funny. I was going to say, make a comment along similar lines, but especially pointing out, look how hard it is to convince people of something that obvious. I mean, when you say, how are you going to make progress? I'm not quite sure what to say. I mean, when Bell writes his paper on the impossible pilot wave, it's very plaintive. It's like, look, even if you don't believe it, it's really important to understand this theory because you can think about it. And it reminds you what it is to have a clear theory, a clear physical theory, and to analyze it and see what it entails, right? And how it deals with experiments and things like that. That you're in a much better position to do any work if you remind yourself what clear thought is. Because quantum mechanics, as it's presented to physics students, isn't a clear theory. It's not clear what it's saying. It's not clear how to understand it. How can you convince people of that? I mean, you can go on shows like this. You can mention that there are nice things they can read that are beautifully written by people who've appreciated that. Are you going to make a dent? I don't know. It's hard. I mean, someone on this particular show, who I will not mention, constantly has the following refrain: the human race is mad. And we can't do anything about that.
Well, maybe the last thing I should ask is what's going on with the JBI, and then we can close out.
It's in a very
the John Bell Institute for our listeners.
Oh, it's in a rather tricky situation now. I've talked to you before. We've been trying to, raise money to get a permanent place, and we have raised money. And thank you very much for everything you've done. Recently, there are just legal issues about the place I wanted to buy, about getting things squared away on the books legally so that a bank would give a mortgage. There's kind of complicated stuff. On the other side, we have an agreement in principle with the University of Split to operate together, and the University of Split has some locations that they could give us to use. And they would help us also maybe find some other locations that might be available for free, closer to where I wanted to be. So the answer is, I don't know right now how it's going to go. I'm still optimistic that we can do something. And there are advantages and disadvantages to different routes. I became very personally attached to the place I found, but it may be that can't work out, or that something better can work out. But I'm in the middle. I'm not there. I kind of only really can interact there in the summers with people. So right now it's a little bit up in the air, how the physical part of that will go forward. I'm pretty optimistic because the people at the University Split were very enthusiastic that we can work something out. But I don't at the moment know exactly what it's going to be.
Good. Well, to the extent that our listeners are able and enjoying these conversations as much as I am, hopefully they can contribute some funds. I'll of course have a link in the description.
The only thing I can say is, look, Shelley's comment about his work with Nino is a perfect example. The people who work on this stuff are very scattered geographically. It's hard to get together. And it's hard to make progress without people who can get together and talk to each other and bounce ideas off each other. And the hope is that this would be a place where that could easily happen, right? Where people could come together in a and have a kind of preset location and talk to each other. And so I think this illustrates why I would think it would help the situation to have a dedicated location for these kinds of discussions, because it's just such a scattered community, and it needs it, right? It needs institutional support. So I'm still going to plug away at it.
Well, this has been another very fun installment of the show. So thank you to both so much for joining me and having this conversation.